Ever wondered why understanding fluid mechanics is crucial for civil engineers? Well, let's dive into that. Fluid mechanics, in essence, is the science of liquids and gases in motion, and it plays a significant role in the field of civil engineering. From the water flowing out of your tap to the sewage systems that keep our cities clean, fluid mechanics is at play. It's the unsung hero in the design and maintenance of water supply systems, ensuring that water reaches our homes under the right pressure. Think about dams, those massive structures holding back colossal volumes of water. It's fluid mechanics that helps engineers calculate the forces exerted by the water, enabling the design of stable and safe dams. What about bridges? The force of wind, a fluid, can cause bridges to sway. Fluid mechanics aids in understanding these forces, leading to the design of bridges that can withstand them. So, fluid mechanics plays a pivotal role in the design and maintenance of many civil engineering structures. Now, let's dive into the properties of fluids. In the realm of fluid mechanics, there are three fundamental properties we need to grasp: density, viscosity, and compressibility. Density, the mass per unit volume of a fluid, plays a crucial role in determining the buoyancy force, which is essential in the design of structures like bridges and dams. Next, we have viscosity. Think of it as the stickiness of a fluid. It's the resistance a fluid offers to shear stress or flow, impacting how fluids behave when in motion. Lastly, compressibility, the degree to which a fluid can be compressed. Most liquids, like water, are considered incompressible in civil engineering calculations. But gases? They're highly compressible, which affects their pressure and volume. Each of these properties has a profound influence on how fluids behave and therefore on the design and construction of various civil engineering structures. Understanding these properties is the first step in mastering fluid mechanics. Moving on, we delve into fluid statics and dynamics. Fluid statics is the branch of fluid mechanics that studies fluids at rest. It's all about understanding how forces affect fluids when they are stationary. One key concept in fluid statics is pressure. You can think of pressure as the force exerted by a fluid per unit area. It's like a crowd of people pushing against a door. The more people, or the harder they push, the greater the pressure. In a static fluid, this pressure acts equally in all directions. Now, let's talk about buoyancy, the force that keeps objects afloat. Picture a ship sailing on the ocean. The weight of the water displaced by the ship is equal to the buoyant force acting on it. This principle, known as Archimedes' principle, explains why objects lighter than the fluid they displace float, while heavier ones sink. Switching gears, we move to fluid dynamics, the study of fluids in motion. Here, we deal with concepts like flow rate and Bernoulli's equation. The flow rate of a fluid is essentially its speed, measured as the volume of fluid that passes through a section per unit of time. Bernoulli's equation, on the other hand, is a statement of the conservation of energy principle for flowing fluids. It tells us that the sum of kinetic energy, potential energy, and pressure energy remains constant in a fluid flowing without friction. It's like a balance scale. If the speed of the fluid increases, its pressure must decrease to keep the scale balanced, and vice versa. All these principles might seem abstract, but they're crucial in civil engineering applications, such as designing water supply systems or predicting how buildings will withstand wind forces. These principles lay the foundation for understanding complex fluid behaviors. Next up, we explore the two main types of fluid flow. First, there's laminar flow, where fluid particles move in straight and parallel paths. Picture a calm river, where the water flows smoothly and predictably. Laminar flow is characterized by low velocities and high viscosity. It's orderly, almost serene, and it's crucial to consider when designing, say, a water supply system. Now let's shift gears to turbulent flow, where fluid particles move in a chaotic, swirling manner. Think of a rushing rapid, wild, and unpredictable. Turbulent flow is characterized by high velocities and low viscosity. It's disorderly and dynamic, and it's especially important in managing stormwater runoff or understanding erosion patterns. In civil engineering, these flow types aren't just theoretical concepts. They're practical tools for predicting how fluids will behave in real-world scenarios. Whether it's designing a pipelines or predicting flood patterns, understanding these flows is crucial. Now, we'll explore boundary layer theory and flow through pipes. Let's dive into the boundary layer theory. Simply put, it's a concept that describes how fluid flows near a solid surface, like a pipe wall. When fluid moves along a surface, the layer of fluid directly in contact with the surface doesn't move due to the stickiness of fluid, or what we call viscosity. This forms a stationary layer, or the boundary layer. The fluid's velocity gradually increases as we move away from the surface until it reaches the free stream velocity. The boundary layer can be either laminar, where fluid particles move in smooth parallel layers, or turbulent, where the flow is chaotic and unpredictable. The transition from laminar to turbulent is determined by the Reynolds number, a dimensionless value that's dependent on the fluid's velocity, the characteristic length, and the fluid's kinematic viscosity. Now, let's talk about the flow through pipes. As fluid moves through a pipe, it faces resistance due to the pipe's inner surface roughness and the fluid's viscosity. This resistance, known as pipe friction, results in energy loss, or what we call head loss. Head loss is a crucial factor in designing water supply and sewage systems. Essentially, engineers need to ensure that the fluid, be it water or waste, reaches its destination efficiently without excessive energy loss. There are two types of head loss, major and minor. Major head loss is due to pipe friction and is proportional to the length of the pipe, while minor head loss is due to fittings, bends, valves, and other such obstructions in the pipe. By understanding and applying the principles of the boundary layer theory and pipe flow, engineers can design more efficient and effective water supply and sewage systems. They can minimize head loss, maximize fluid delivery, and ensure that our daily life runs smoothly. These are key concepts in designing efficient water supply and sewage systems. Finally, we delve into dimensional and model analysis. This might sound a bit complex, but stick with me, it's simpler than you think. Dimensional analysis, at its core, is a method that simplifies complex problems in physics and engineering by reducing the number of variables. It's a bit like decluttering, really. You know how it's easier to find your keys when there's less stuff on the table? That's essentially what dimensional analysis does with variables. Now let's think about a civil engineering project, like designing a bridge. There are countless variables to consider: material strength, wind speed, traffic load, and so on. Dimensional analysis allows engineers to focus on the key variables that will have the most impact, making the problem much more manageable. Moving on to model analysis, this is a way of testing designs before they're built. Let's stick with our bridge example. It would be impractical, not to mention incredibly expensive, to build a full-scale bridge just to test if the design works. Instead, engineers construct a scaled-down model of the bridge. They then use this model to test different scenarios, like high winds or heavy traffic. What's important here is the scale. If the model is, say, 1/100th of the size of the actual bridge, all the forces applied during testing must also be scaled down by the same factor. This ensures that the results from the model can be accurately translated to the real-world structure. So, in essence, dimensional analysis simplifies the problem, and model analysis provides a practical way to test solutions. Both methods combined allow engineers to make informed decisions about design and construction, reducing costs and improving safety. These analysis techniques are invaluable tools for civil engineers, helping to predict real-world performance and optimize designs. To sum up, fluid mechanics is a fundamental pillar in the study and practice of civil engineering. It's the science that deciphers how fluids behave, and it's the knowledge that enables us to design and construct structures that interact with fluids. We've journeyed through the properties of fluids, understanding their statics and dynamics. We've seen how different flow patterns, laminar and turbulent, impact the design considerations. We've explored the boundary layer theory and how it influences the flow through pipes. We've delved into dimensional and model analysis, a vital tool for simulating real-world scenarios. All these concepts and principles form the bedrock of fluid mechanics in civil engineering. They enable us to create marvels like towering dams, efficient sewage systems, and sustainable water supply networks. And so, we conclude our journey with a newfound appreciation for the unseen science that shapes our world. So, the next time you marvel at a towering dam or a smoothly flowing sewage system, remember the role of fluid mechanics in making it possible.